Okay, welcome to another week of the semester. I believe it's week number 4. We are still doing introductory parts of machine learning. We have covered an overview of machine learning. We have covered a little bit of linear algebra. And today we're going to do a little bit of polynomial curve fitting, which is an introductory topic in regression. Now, before I begin, are there any issues that any of you wanted to bring up after last week? Okay, so you can send me chat messages if you want. Are there any pending items? And we will take care of that before we move on. Now, today we are going to have a quiz at the end of the class that Mihir and Saugata have worked on, and their questions pertain to last week's lectures. Both last week's 2 lectures concerned linear algebra, where we talked about basic ideas: scalars, vectors, matrices, tensors, matrix multiplication, matrix inversion, how you can solve for a set of simultaneous equations using linear algebra. So I think they have worked on those topics, and that's made available. Okay, so anyway, they'll conduct that at the end. Mihir will tell me when we should stop. Uh, Today we're going to start with a topic called curve fitting again. So this comes in if you want a book version of it, you can find it in the Chris Bishop book. He has a nice description of curve fitting as a first topic. He actually begins the book. Let's begin with curve fitting. How would you do curve fitting? If I give you a set of points of input-output pairs, how would you fit a curve so that I can use that curve to predict for any future input what is the output? So that's the kind of problem we look at, right? Okay, let's see. There is one question. What should I prepare for this class in terms of Python? I completely lost in last week's breakout sessions. All right, Mihir, you want to take that up? You want to answer that question?
Yep. In terms of Python, you should be only familiar with the basics of Python. Python notebook was shared with introduction to topics.
Mihir, are you still there? Okay, you went suddenly.
Yes, I'm here. I think there was some noise from some of the participants, but I've already shared a Python notebook which covers all the basics of Python, and that's all is which is required for solving breakout session uh, problems.
Uh, Kurt, you can also take advantage of the office hours that both Mihir and we are fortunate to have Saugata as well. I don't know if he's here today because he's got another class he's TAing for exactly at the same time. So I think he divides his time between this and that. So they have announced their office hours. If you're feeling really lost, reach out to them by email or in their office hours that they've specified. And Mihir is an excellent teacher. He's always got rave reviews from all students. So Saugata, he's a new TA. I'm sure he's also extremely diligent, and we are there to help you out. Okay. All right. Any other questions? All right. Very good. So we have a full class today. Happy to have all of you. And so we're going to begin with curve fitting. And before I put up my slides, actually, I have made the slides available in UB Learn. So what I try and do is I also review the slides a little bit before class and says, okay, we're going to go over this. And then I put it up in UB Learns in the course document section. But if you want a little bit, earlier preview, you can just go to my public site and you'll see what's coming up next. So I think after curve fitting, it's going to be probability theory. Again, basics. I'm deliberately going a bit slow on the on the on this material, because I feel this is really time well spent, because there are a lot of machine learning techniques, one after the other: method A, method B, method C, method D, etc. Like so we could run through all of them, but I think it's important to get a feel for what are the issues here. And then if even if you don't cover every method of machine learning, you know what we're trying to do. So that's what I'm focusing on. So we might be going a bit slower than usual, but deliberately so, which is time well spent for you. Okay. All right, then. So we're going to do curve fitting. All right. So let me start sharing my screen on the slides. And that one is... I'd minimize that, and it's not showing up. Let me try again. Oh, there we have it. Okay, this one is titled Polynomial Curve Fitting or Curve Fitting. What it is a particular approach to curve fitting, a simplistic approach, good only for a simple problem, which is a one-dimensional problem. One can use polynomial curve fitting. It is not applicable to input, which is multidimensional. Almost all machine learning is multidimensional, multivariate. Polynomials are good only for, like, if you have like one input variable and one output variable, then you can use this idea of polynomial. Then why do we study polynomial curve fitting as a starting point when you can't use it for more dimensions? I mean, in principle, it could be used in some kind of generalization. It doesn't come out very nice. So it's only good for one-dimensional problems. We'll look at it because it introduces the ideas of loss function and minimization, and also the concept of regularization, and the issue of model complexity. These are all deep issues in machine learning. All of them come out in this problem alone. So you get a sense for what do you mean by loss function? What do you mean by taking the derivative of the loss function? What do you mean by regularization, and why do we need that? And also it ends up using linear algebra solution to the problem also. So this is what we will look at as our first topic. Okay, so you would not be using polynomial curve fitting as a solution to some regression problem where you have many input variables. So keep that in mind. So it is just an introductory topic which kind of helps us run through different ideas. All right, so the topics here are a statement of a simple regression problem. And then we state what the problem is. That is, we have a set of input points and the corresponding set of output points. And we have this idea of polynomial curve fitting. So if I plot the y values against the x values, you have a series of points. And how would you fit those series of points is the question. And I would draw a smooth curve. And if it is a little bit more complicated, then maybe we'll go to a higher order polynomial, which is not a very smooth curve, but it's got some undulations, goes up and down and so on. And then we introduce the idea of a little bit of probability theory of multiple variables apparently comes in here, where we talk about noisy samples and so on as well. And then we'll talk about maximum likelihood solution and the Bayesian approach. Okay, so this is covering quite a range of things. So just in this lecture, let's say how we do all of this. Bayesian approach and the model selection. Model selection has to do with things like degree of the polynomial. Do you want a linear fit, or do you want a quadratic fit, or a cubic fit, and so on? And which one would you use? That's the problem of model selection. And then the cursive dimensionality, what happens when you increase the number of dimensions. Okay, so let's look at a simple regression problem. The reason we look at it is it motivates a number of key concepts, as I mentioned already. And the problem is we observe a real valued input variable and then use that input variable to predict the value of a target variable, right? So we are getting some input from a sensor. Robot is moving and it is seeing some input coming into the radar or something like that, right? I was reading something today about how they're programming robots, a swarm of robots or a swarm of drones and things like that. Let's say there's only one value coming in, not a whole image or anything. One value. Maybe radar product provides one value. How close you are to something is just a single value, that's X. And we want to use that to predict the value of the target variable T. T is maybe, what direction should the robot move, or what direction should the drone move, or something like that. So it's a very simple input-output relationship with one input variable. And we consider an artificial example using synthetically generated data. So the example given on the next slide is going to be the input-output is synthetically generated, not from some real drone or a real robot, but it is something, let's say the input-output relationship is sinusoidal. So if X is the input, T is going to be sine X. All right, so that could be a simple input-output relationship where we use that sine X model to generate samples. We take several values of X, and for each value, we generate a value of sine X. So we create a table saying, okay, here is some data. And then we now challenge our machine learning program. Can you figure out what is the relationship between X and sine X? The program, of course, doesn't know that it's coming from sine X, that's synthetically generated, but it has to make a good guess that is very close to it. So here is a synthetic data for regression. Data generated from the function sine 2 pi x. All right, so this is a little more complicated than simple sine x. It's sine 2 pi x, where x is the input. As you can see from the picture, sine x is sinusoidal, right? That is the famous sinusoid that comes from the sine function. And as the input x varies from 0 to 1, sine 2 pi of x oscillates between +1 and -1 like that. It goes from 0 to 1 to -1 to, right, so on. So this is a relationship to the angle, I suppose, 2 pi x. Pi goes from 0 to 360 degrees, right? So on. So that's what happens to the sine function. And input values x sub n generated uniformly in the range 0 to 1. So let's say we wanted to give the machine learning program some samples. And rather than give an infinite number of samples as input, we select some small number. You see the blue circles here. You can say these are all the examples that we give. We have only a few examples. Let's see how many, 3, 5, 7, 10. There are only 10 data points. And we uniformly generate samples in the range 0 to 1. And let's say that created these 10 samples. And so we now have values. We give to the program saying for each xn, what is the value of tn? We not only do sine 2 pi of x, we also add random noise with a Gaussian distribution with standard deviation 0.3. As you can see, sine 2 pi of x will be this perfect green sinusoid, but these blue points are not lying exactly on that green point. They're a bit off. And they're a bit off because after every sine 2 pi x was generated, we add to it a quantity, a Gaussian distribution, which is usually centered. A Gaussian distribution, a standard normal distribution would be centered at 0. It can take values which are positive or negative. And we can specify as to how much they are away from the mean, and that is chosen by the standard deviation of 0.3. So sometimes the values will be positive, sometimes they'll be negative. And so, which is why you can see sometimes the points are above the curve, and sometimes is above here, above here, above here, and sometimes they're below as well. So this is, we call this as a synthetic data set, because we just want to see how well our machine learning program will do, and how do we have to set its parameters to do this as well as possible. So you can think of it as this is a standard problem, and this is called regression problem. And so let's look at the nature of the training data. So I think this slide is a repetition of what we just said. We have n observations, x1 through xn, and the outputs are t target variables, t1 through tn. We show these as a vector here of, that's why we have a transpose here. It's a column vector, t is a column vector. And goal is to exploit the training set to predict a value t hat for some new value x hat, right? So when I give you a new value for some new value, which is not in the training set, it's being distinguished from the training set as a x hat value. So we are predicting some t hat from that. And we're saying this is inherently a difficult problem to be able to predict it, because we don't know it's coming from sinusoid. We just have the samples. And the way we are going to solve it in machine learning is probability theory provides a framework for quantitatively expressing uncertainty, right? And decision theory allows us to make a prediction that is optimal. So probability theory will give you some probability distribution of what the output should be. Decision theory says, what you could exactly choose from that probability distribution, and so on. So these things come into play. So let us look at the simple polynomial fit. So let's say we don't know that this data is coming from a sinusoid, and we are told that it could be some kind of a smooth curve we'd like to draw. And we could say, try and use a polynomial function which has got this form. We say y of x comma w. W is a set of parameters. X is the input, y is the output. So we kind of show the relationship between y and x. Y is not only a function of x, but it's also a function of parameters. And what are these parameters? Is w naught plus w1x plus w2x squared plus wmxm. We are saying x is your input. We take the linear x and the squared of the x and to m to the power of m of x, and we weight all of these together and we add them all up, and I can show it as an abbreviation, j equal to 0 to m wj x to the power of j. It's exactly the same thing as this. So it is j equal to 0 through m. So we're saying, what if we allow our output to be a sum of all these powers of x weighted by some quantity? Of course, if we did not allow higher order polynomials, w0 plus w1x, that is the equation of a straight line actually. So you can only fit a straight line to the data. Straight line will not be good enough for a sinusoid. We need fluctuations going on. So, so just using w0 plus wnx is not good. So if you chose just w0, it will be some kind of a fixed straight line, horizontal line. This will give you a w0 plus w1x, allows you a straight line that is at an angle also, w0 plus w1x. w0 plus w2x squared could give you a little bit more complicated, but x squared term says it is some kind of a quadratic. Quadratics are the curves that can draw things like parabolas and hyperbolas and and so on. So you can get, but there's only a certain degree of complexity with a quadratic also. Sinusoid is a bit interesting. It is a little bit more complicated than that, perhaps, and it may not lie. But and we can go up to some number m, which is the reason they've chosen the letter m is it refers to model complexity. M is the order of the polynomial, but m is also the order of the model complexity. How complex do you want your model to be? And so they say, okay, you are choosing what is the degree of the polynomial and you're fitting that. Then we ask the question, is higher value of m better? We'll see shortly. Okay, actually, it is putting you in suspense as to what is the value of m you should choose then. And then we'll argue that too low a value is creates what's called as bias in the sense it can only give you a very biased output, in the sense it can only give a straight line. So it is kind of very hard to change opinion. It's a very simplistic biased system. It's like somebody who won't change their mind at all. And when you chose a value of m equal to a low value, you're going to get a biased output. But if you choose a high value of m, it is not biased. It's very, very flexible. You can draw all kinds of curves running through those points, going up and down, and even exactly fit the data points. The problem with it is it's not going to have a bias, but it's going to have what's called as variance. Okay, variance comes about saying, well, with new data points, and if you measure how close the output is, it's going to have a lot of variance over all different types of data you're going to have. So this is famously called in machine learning as the bias variance problem. So if you have a low degree polynomial, you have a high bias. If you have a high degree polynomial, you have high variance. So a lot of the techniques in machine learning argue between bias and variance. These are statistical concepts. And it's good to know what is this trade-off between bias and variance. Anyway, I kind of jumped the gun, and I'm answering the question, is higher value of m better, although it says we'll see shortly. All right. Coefficients w through wm are collectively denoted by the vector w. And we say that w is a nonlinear function of x we are saying x squared and so on, but a linear function of the unknown parameters w. So we have a linear function of these parameters. And these are called as a linear models. Okay, so we're just weighting all of these. We're only talking about polynomials here. Although polynomial, as I said before, is not the common solution to multidimensional data. Multidimensional data would say x is not a scalar value, but it's a vector, in which case, what is complicated is x is a vector. What do you mean by w to x squared? What do you mean by square of a vector or to the mth power of a vector and so on? I mean, you will have cross terms and so on between the dimensions. It gets awfully messy if you try and take a polynomial function defined for a scalar value x, replace it by a vector value. So we don't use this polynomial method, as I said before, but we'll just stick with a scalar value for now and see what else can we tell about. Yeah, was there a question or something? All right. I can't see the chat session. Mihir, please let me know if there are some questions there. Okay. All right. So I guess that's a simple approach. Okay, let's go to the next slide. It says, well, if you're going to be learning these values of W, we'll have to figure out what is the criterion to determine our choice of W. So one of these, an arbitrary choice I'm making here, is let us use summa squared errors. That is, you remember those blue circles and the green curves there and so on. So we say, well, how much off are you? The target has a certain value Tn for each value of Xn. And we say the model is Y. We say that we call this as a model because it is the one that's the predictor. And we say it's a function of Xn, the input, and it's also a function of the current set of weights that you got, W. And so we take what is the model saying as to the output, and we take the difference with the target value, and we take the square of the difference, because it can be positive or negative values, right? Square will make it all of the same sign. Square of a negative number is also positive. And we add it over all the set of samples n over here. And that we refer to as the total error over all the data points. And we multiply it by 1/2 and, refer to it as EFW, that is the error associated with W. All right. So the factor 1/2 is included for later convenience. What is this later convenience? Is we're going to try and minimize this quantity. So that is where the maxima minima come into play. Even for this polynomial curve fit, calculus has to come into play, because we're saying what value of W is going to make this as small as possible. And so to find that value of W, we're going to take the derivative of this quantity with respect to W. Remember that we have uh, this equation here, it's a square here, and we take a derivative with respect to W. Well, how do you take with respect to a vector derivative? We'll have to take partial derivatives with respect to all the W's. We have W0, W1, W2, W3, right? So we'll take partial derivative with respect to all of them. And we have to set them all equal to 0 and solve for the W's. And we'll say, okay, for it to be the error to be minimum, the derivative has to be equal to 0. Okay. So we say solve by choosing the value of W for which this is as small as possible. And red line is best polynomial fit. So if you're talking about a polynomial fit, if you have a points here, we're only showing 3 points, and say, okay, what is a good polynomial fit for some degree polynomial? It's some kind of a fit that's being obtained here from that W. Okay. So let's now look at minimizing the error function. We say that the error function is a quadratic in coefficients W, because we are going to be taking square of this vector W. Derivative with respect to coefficients will be linear. Now we take derivative. What does derivative of this look like? So this gets into the calculus that we need. We say that since y of x comma w has this form, all right, so we have summation over n samples here. But remember that y itself is a summation over all the weights m. So you see there is an n over here, there is an m over here. N is the number of samples in the data, m is the number of model parameters. And so the derivative already looks a little bit messy. This is a partial derivative. This is this kind of a curved delta. Partial derivative of EW with respect to WI, one of the weights of this derivative of this quantity can be written as that same quantity, and we are now writing it by expanding it out, and then we say there is this quantity here, and that is the nature of the derivative of this. So we're saying the derivative doesn't have the square anymore. You see, the 2 is gone there, and this 1/2 is gone also, because 2 and 2 cancel out. And so this has become this quantity here, and there's an xn coming over here that comes from the basic calculus of a derivative of a square of a function. All right, so there is this difference. That difference is from here. There is also an xn that is the derivative of this quantity over here. And because the w is gone, you're taking the derivative with respect to the ith variable. That's why the xi remains. The rest are all gone. Partial derivative means they're all zeroed out. There's only this quantity. And then that's being rearranged over here like this. And we say this derivative is now set equal to 0, and we get an equation of this form. And this turns out to be a set of m+1 equations over m+1 variables. That's good. We are looking for m+1 m+1 values. So we have m+1 equations over m+1 variables. They're all simultaneous equations, which we need to solve to get elements of W. Oh, wow. So you see, just let me go back to the previous slide. Just to get hold of all of these w's, we're going to set the derivatives of all of these partial derivatives, and that gives you a set of simultaneous equations. We need to solve all of it. That's going to give you the w's, and that is going to be your answer. All right. So this problem of linear regression, without doing anything more, just to say how are you going to get the w, and we're even using a simple model called a polynomial, that's already giving us this issue of solving simultaneous equations. And so we can now focus our attention on solving simultaneous equations, which is why I wanted to go over some linear algebra in the beginning. That same linear algebra is being used here. So if you're going to have a set of simultaneous equations, which are all produced by taking the derivative and so on, and how would you solve for it? And basically, after you set up on the previous slide all the simultaneous equations, you end up with a matrix formulation of the simultaneous equations that look like this. A is n times m plus 1. So you have to, this A is a newly set up matrix which consists of n rows corresponding to the n data samples, and the columns correspond to the m plus 1 parameters. So we refer to this as the design matrix of the data samples. So that is the design matrix which captures all the samples you have and all of the parameters that go with it, and that's what we want to solve. And then W is the set of weights to be determined. So this is the design matrix, and this is the values of the outputs corresponding to them. So this kind of stated generally in multi-dimensions now, and then we can solve this using matrix inversion. W is equal to A inverse of B, so on. So that can be applied to this problem. And we already saw this slide, I think I introduced it before, that if you have a matrix formulation, you can solve it using matrix inversion, or you can use Gaussian elimination and so on. So the problem can be solved in these ways. Okay, so that was just about what it takes to solve a set of simultaneous equations and solve the regression problem using that. So let's then look at what should be the degree of the polynomial. And here we have the order of m, choosing the order of m. So if we choose m equal to 0, then we'd be fitting this red straight line to this set of points. It's a straight line, it's not even tilted. If you choose m equal to 1, this would be just w naught, this would be w naught plus w1x. You can get a red line like this. And you just need to choose the parameters w naught and w1 to specify this red line. If we choose m equal to 3, which is what we called it as a cubic, the cubic gives you a fairly good fit. It's not quite a sinusoid. So you're saying it's w naught plus w1x plus w2x squared plus plus w3x cubed, okay, something like that. So this would be kind of fit you could get. But what if I said, look, what if I choose m equal to 9? It's a very high degree polynomial. Then you have this red line is going through all of the data points exactly. So it's fitting these points very, very well. But then you ask yourself the question, is this a good fit? It's perfectly fitting your data points, but when you compare it to this green sinusoid, you can see what a poor fit it is. So we say that this model is not a good generalization, which is, what do you mean by generalization? It is whether it is a good fit for data you have not seen. Of course, we don't know that it is coming from a sinusoid, but such an exact fit is most likely not going to be a good answer. Right? You might actually be better off by having a very low model complexity. But an ideal complexity is this one, m equal to 3. This seems to be almost equal to a sinusoid. So this is the issue of choosing the right order of model complexity to fit the data well. Okay, so then comes the issue of how well the system is performing. I think in some of the breakout sessions you got introduced to this idea of RMS error and so on. So what it is here is consider a separate test set of 100 points, and for each value of m, evaluate these sum squared errors for each value of m. And they're plotting here, m is the model complexity, which is going from 0, 3, 6, 9 degree of polynomial. And you're computing not EW star, which is the standard definition here of the sum squared errors. We are using so-called RMS error, which is 2 EW star divided by n square root of that. What is this peculiar thing here? This is saying don't use the error as such here, but you divide it by n, multiply it by 2, and take the square root of that. Why are you doing that is division by n allows different sizes of n to be compared on equal footing. Otherwise, this error is going to grow unbounded with n, the number of samples. When you have lots of samples, the error is going to grow. When you divide by n, you're gonna make it proportional. And square root ensures ERMS is measured in the same units as t. So anyway, this mechanism is being used here. So we are plotting here ERMS, and we are running it on an average of these 100 data points, which it has not seen, referred to as a test set. And as you can see, as the degree of the polynomial keeps increasing, the performance on the test, this is a performance on the training set, is the blue one. And the error is going down and down and down. It's exactly fitting, and so it's zero error with degree polynomial 9. But as we go along with the test set, it's also going down and down, and it's kind of stabilizing over here. And when you get down to something like m equal to 9, suddenly the error here shoots up, because you have chosen such a high degree polynomial that is exactly fitting the data. It does very poorly on the test set. So we say that a high degree polynomial has very poor generalization performance. And we refer to this thing of fitting the data exactly as an overfit. So in machine learning, we say that we do not want to overfit the data. Overfit the data is equivalent to memorization of the data. And memorization is good to answer it exactly when you give me the same examples. But if I give you other examples, it's going to do poorly. So this introduces the concept of test set, training set. Performance on blue is the training set. Performance on red is the test set. And it also introduces the idea of model complexity and its relationship to generalization performance. Another point that is being made here is they ran this data on this linear regression problem. And what they did was obtain the values for the parameters W0, W1, W2, up to W9 for a degree 9 polynomial as well. And they are now for each value of m, m equal to 0, m equal to 1, m equal to 3, m equal to 9, they are plotting the values of the w's. Okay, so for m equal to 0, you need only w0, that was 0.19. For m equal to 1, you need two parameters, that is w0 and w1, that is 0.82 and minus 1.27. Then they said, okay, what if we choose m equal to 3? You'll need w0, w1, w2, w3. The values for 0.31, 7.99, minus 25.43. So you see, these would be the values that you would need for that same data set. And they said, what if I make m equal to 9, ninth degree polynomial fit? You see the w's, how they change. 0.35, 232.37 minus 5,321, 48,568. This is what? 231,639, 64, right? 640,042. This is, look at this, W6 minus 1,061,800. W7 is going to be 1,042,400. W8 is again 55,000, right? 557,000, 125,000. It's really interesting. We had this only like a 10 data points we had to train on, and we were trying to fit them, and we are trying here different degree polynomials, and it's coming from a simple problem. 0 to 1 is the values of the input, and the output we saw is the value of sine 2 pi f x, and these are astronomical figures here. 1 million and so on. I mean, very quickly, we're getting huge numbers. As m increases, magnitude of the coefficients increases. The magnitude means how big these numbers are. This is kind of small magnitude, lies between 0 and 1. This is lies between 0 and, let's say, minus 2. This lies between minus 25 and plus 17. This is horrendous, m equal to 9. At m equal to 9, finely tuned to random noise in target values. We did have noise in the data. It is finely tuned to fit all of that noisy points. So this brings in an important lesson to the machine learning part, which is, when you're trying to fit, you don't know what degree of polynomial you want. Don't allow the parameters to become uncontrolledly large. Control it by keeping it, somewhat manageable. All right. This brings in an idea of regularization in machine learning. It says, other than minimizing the sum of squared errors over the samples, you also minimize the length of the weight vector. All right. So you see the length of this. Supposing this is a 9-dimensional vector over here. This is what's the length of this vector? It's going to be pretty large. Some components are minus 1 million and plus 1 million and so on. And if we compute the length of this vector in that 9-dimensional space, it's going to be pretty large, of the order of thousands or even hundreds of thousands will be the length of that vector. And so we want that length of that vector to be kept small, which is the idea of regularization. Okay, so that will come up again and again. It's called the norm penalty. Norm, yes. We just saw what is in matrix terminology, what a norm is. Norm is the length of the vector. We said there's going to be a norm penalty, that the solution you come up with should not have a high norm. Okay, norm. Okay. All right, increasing the size of the data set. So what if I increase the size of the data set? For a given model complexity, overfitting problem is less severe as size of data set increases. So supposing I had, this one had 15 data points, n equal to 15. So instead of just 10 points, a lot more blue circles here. And now I'm using n equal to 15, and I'm using some higher degree polynomial, which is not just a cube. You see how curved this red line is. So this is obviously more than the cubic. It is the cubic was fitting the sinusoid exactly. This is fitting the data even more on the noisy points, and so it gets a solution like that. And what if we had lots of data points, n equal to 100? If you have n equal to 100, the red curve almost becomes a sinusoid again. All right, so it's interesting that the model complexity is somehow related to the amount of data that you have. So if you have a small amount of data, then you can only use a small model complexity without running into severe problems with overfitting. But if you have a large data set, you can afford to have much more parameters. All right. So what is a rule of thumb? Data should be no less than 5 to 10 times the adaptive parameters in the model. We refer to those W0, W1, and so on as adaptive parameters. Some rule of thumb is being said here that if you're going to have um, 5 to 10 times, so if you're going to have you know m equal to 9, then you should have at least 90 samples or 100 samples. So in this case we have 100 samples here, and we are still using m equal to 9, so it's fitting fairly nicely. But if you have only 15, there's going to be some degree of overfitting that's going to go on. So there are some interesting relationships here between model complexity as well as the size of the data set. So let's see, least squares is a case of maximum likelihood. So the question obviously you can ask, where did you come up with this idea of sum of squared errors? And that sum of squared errors emerges from this probabilistic principle called maximum likelihood. And we can derive it by saying if that noise model was Gaussian and you take that into account, and now you solve for the problem, you end up with saying, the solution is a sum of squared error. So I think this was a question I brought up on the first week of class, that the so-called loss functions end up being sum of squared error. And why is that? Because of the maximum likelihood principle. And anyway, so that's again being repeated here. And we say that the least square, we call that as the least squares approach, is a specific case of maximum likelihood. And overfitting is a general property of maximum likelihood solutions. In maximum likelihood solutions, where we're using sum of squared errors, we saw that an overfitting problem can arise. And an alternative approach is called the Bayesian approach. And the book by Chris Bishop emphasizes this Bayesian approach, avoids the overfitting problem where the number of parameters can greatly exceed the number of data points. And you can still get a reasonable solution by working with what are called as prior distributions of the parameters and so on. So that's, we don't want to go there too much. Let's just mention that Bayesian at this point. So now let us explicitly state what's called as the regularization of least squares. We say, instead of having the sum of squared errors, which is the y minus t squared over all the n samples, we add one more term, lambda by 2, the norm, squared Euclidean norm, we call it, of w squared. This is the length of the vector. And what is this w to this? A precise definition is being given here. It is nothing but w transpose w, which is equal to w naught squared plus w1 squared wm squared. That quantity is a measure of the squared Euclidean norm. That's what we say. That's what this is. And what is this lambda? Lambda determines the relative importance of the regularization term to error term. So now we say that this loss function, which is a generalized error function, has two parts to it. One part is the sum of squares. The other part is the length of the squared norm. And this quantity can be minimized exactly in closed form and known as shrinkage in statistics and weight decay. So in neural networks. So this is referred to as weight decay is the term that is used. Now, this diagram shows the effect of the regularizer. So we are saying what happens when you control that lambda? If you use lambda equal to 0, which means don't use that regularization, then you're going to get exact fit like this. And we are using a ninth degree polynomial here, m equal to 9. So even though we are using a high degree polynomial, by using a regularizer, if you use a very large regularizer, lambda is, in this case, log lambda equal to 0. They're showing everything in terms of logarithm of the lambda here. Then the fit is going to be biased. It's going to be this red line, which is not a very good fit. In this case, what's happening is you're ignoring the error and you're controlling it by only the regularization term. And if you're using some lambda in between, you're going to get a fairly good fit, even when you have a small number of data points. So the regularizer is a very interesting concept that if we use a 9th degree polynomial and we use log lambda equal to minus infinity and log lambda equal to 0, this is log lambda equal to 0, and this is something in between. So we are saying here the values are all extremely small, log lambda, which is equal to lambda equal to 0. So log lambda equal to 0. And no regularizer. Okay, I'm sorry. The log lambda is equal to minus infinity when lambda equal to 0. This is this column here that corresponds to this part here, which is having no effect, which is equal to lambda equal to 0 or log lambda equal to minus infinity. And the and the other end is an extreme bias. This is log lambda equal to 0 over here. All right, and this is something in between. You see the length of the weight vector here. This is 0.35. This is not too large. This is too large, the magnitude of the vector. This is too small here. This is something in between. So that's the Goldilocks regularizer here. So you see there is all this kind of control that goes on. The effect, regularization is a big topic in machine learning. There are many, many methods of regularization. This is the norm penalty regularization that this curve fitting problem introduces. And then we study a number of methods, particularly in deep learning. There are many, many ideas, and a lot of research goes on in how to come up with good regularizers, which means better fitting or better generalization. Um, so, so let's see, what is the impact of regularization on error? And so they say lambda controls the complexity of the model and hence the degree of overfitting, analogous to choice of M. And an approach to selecting, now then these are called, lambda becomes what's called as a hyperparameter now. And M is the, or the model, number of model parameters, that is also a hyperparameter. So they're showing here that how do you figure out what should be the value of lambda? And one way to do it is to run through different values of lambda. They're going with log lambda. It is minus 35 to minus 20. And they're computing the ERMS over here. And on the training set, as you keep increasing lambda, the error keeps increasing here. And whereas with the training set, with the test set, it goes down. And so you kind of figure out so it doesn't go back up again. You want to keep ERMS as small as possible. And so you find some point here, which is where we fix the lambda to be somewhere over here, corresponding to the lowest point of the RMS error. So we do this on a test set, which is referred to here as a validation set. So you're not doing it in the final test set that you're going to be using, but only on a holdout. So you use part of the data for training the model and another part of the training data, which is held out, to determine the validation set to figure out where you should set the value of lambda. So this can be used for optimizing model complexity, M or lambda. You can try different degrees of the polynomial, or you can choose different values of lambda. Which brings us to the summary of curve fitting. So partitioning data into training set to determine coefficients W, and a separate validation set or holdout set to optimize model complexity M or lambda. M is the model complexity, degree of polynomial. And lambda. Now, keep in mind that we are talking about a model where the input is scalar value. Model complexity was determined by the degree of the polynomial. When we move to other models where we are dealing with vector inputs, as we will do with linear regression, using non-polynomial methods, and there we will, the model complexity is again set by the number of parameters that you're going to be using in a different way, not necessarily as a square and so on, or powers. So more sophisticated approaches are not as wasteful of training data, and more principled approaches based on probability theory. Probability theory is going to play a role. And then classification is a special case of regression where the target value is discrete values. Okay. All right. So that brings us to the close of this particular section on curve fitting. All right. So, are there any questions on the lecture of today? Okay. Mihir, are you still there?
Yes, Professor.
Okay. So, do you want to take over at this point?
Yes, so we can start with the quiz now.
Okay. So, why don't you say generally how you're going to do that?
Okay. So I have made the quiz available on UbiLearns. Just open up UbiLearns, go to your course, CSE 474 or 574. Under quizzes section on the left, you'll be seeing a quiz